Welcome to the New Calculus channel. I am John Gabriel, and in this lesson we will be looking at the derivative, which is really a method of finding the slope or the gradient of a tangent line. So in the last lesson, which is quite short, we looked at secant and tangent lines and examined the relationship between a set of parallel secants on a small interval and a tangent line. And we noted that for all those parallel secants, the tangent line is related through an auxiliary equation, which we did not discuss in detail because we will discuss that at a later stage. So in this lesson we will see how to find the slope of tangent lines. Let's begin with the first applet. Okay, here you see a parabola, and what you have here is the point of tangency and the parallel secant here. This is the parallel secant and the tangent line here. And all you really have is the rise, which is 3.01 divided by 1, yes, and that gives you the slope. Now, if you use the definition of derivative in the new calculus, which is f of c plus n minus f of c minus n over n plus n, you will arrive at 2c plus n minus m minus 4, and that's the exact slope. And if you substitute the values for c plus n, c minus m, and everything else, c, n, and m in here, you will get the gradient, which is 3.01. Now notice that m is the horizontal distance from the apsis of the point of tangency to the lower endpoint, or one of the endpoints of the secant line, this point here. And n is the other distance to the other endpoint. Now, m and n in the case of any parabola are always equal, but this is not true for any other curve. In fact, it's not true for most curves. It may be true for one or two other curves, but it's not true for most curves. The relationship between m, n, and c is called the auxiliary equation, and it's denoted by q with these three parameters, c, m, and n. Now you'll notice that as the secant line gets close to the parallel line, both m and n become pretty close to 0. Yes, so it's very easy to prove that the auxiliary equation is equal to 0, but that's not the purpose of this particular lesson. All I'd like to do is just get everyone up and going on the new calculus derivative, which is this here. The auxiliary equation here is n minus m is equal to 0. And since n and m are always the same, it doesn't matter what they are. As you can see here, 1.3 in this case, 1.6, 2, whatever. It's just the same number minus the same number, which means this here is always 0, so it'll just be 2 times 3.5 minus 4, which is the gradient. Okay? So you can move around and see the results of moving it. For example, over here at 2.5, the slope of the gradient is 1. Let's just look at the notes. M plus n is always a factor of the numerator, this numerator here, f of c plus n minus f of c minus m, regardless what is f of x. That has been proved in an article here on the New Calculus. In these first 4 articles, there is a proof of that, and there is an even simpler proof using the Gabriel polynomial, but that's quite advanced. So it's actually easier to prove in a few lines, but you have to know a lot more to prove it. So that's another way of proving that, in fact, m plus n is really a factor of every term in the numerator. Neither the secant line nor the tangent line slope depends on m and n. So it doesn't really matter what m and n are. That's not going to change the slope of this tangent line. All it does is it just basically gives us those 2 points from which we can calculate the slope of the parallel secant and hence the slope of the tangent line. Turns out that we don't really need to know m and n at all, but there are many m and n pairs. At the point of tangency, right over there, m and n are actually 0, but they don't have to be. Any m and n in this equation here will still hold true and will not change the value of the gradient. M and n have a special relationship that is represented by the auxiliary equation. The auxiliary equation is this QCMN parameter. There are infinitely many mn pairs that will satisfy this formula, this equation, which we use to find the tangent line slope. Let's look at the auxiliary equation very quickly. Probably before we do that, let's just look at the derivative once again. Here's the definition, the new calculus derivative. Okay, so let's suppose that we can move the tangent line like that, and we know that the actual value is 13.5, but if we just move that to get the other endpoint of the parallel secant, you see it's actually getting closer to the value to the actual value. So, and there it's pretty close, as you can see. We can also move that away and move that away, in which case we'd have to bring that back on the curve to get approximately the same value. You can experiment with this applet and see the calculations working. You will notice also that there is always a set of parallel secants to a given tangent line. Let's take a look at the auxiliary equation. Now, remember in the first applet we looked at the parabola, which is really a simple curve. In this one here we'll look at the cubic curve, and we see that the auxiliary equation is quite different. Can you see down here? Instead of saying QCMN, I've said QXMN, but it doesn't matter because X means the same as C here. And this here is the auxiliary equation, which is equal to 0 always for this cubic, which you see down here, x cubed minus 2x squared minus x plus 2. And so, you can move this particular yellow point here on the tangent line and see how these values are affected. All the values of m and n are related, and they're also related to the point C of tangency, to this point here. So if you move the value of m, see, the value of n will also change, and as you get closer to 0, obviously both of them are going to eventually be 0, and you'll have what is required for the point of tangency. This is not a limit. In fact, no limits are being used here whatsoever. There's no concept of infinity. It's a very simple geometric scheme, so it's based on sound analytic geometry. This trapezium here really kind of summarizes the whole idea behind the concept, and we can also see what happens as we move this tangent line towards the point of inflection. There's no longer trapezium there. Okay, when that happens, as you can see, it's Q here is indeterminable, although that is the auxiliary equation. In the new calculus, in order for a curve to be differentiable at the yellow point, it must be both parallel to at least one secant, and Q of x m n must equal to 0. So those two conditions are required. If only x m n is equal to 0, as in this scenario, then that's not sufficient to say that x is in fact differentiable at that point, because watch what happens at the point of inflection. It is equal to 0 if m and n are 0. Do you see that? So you need those two conditions in order to say that it's differentiable at a given point. Okay, and so those three applets give us an idea now about this basic definition of the derivative in the new calculus. Notice there are no limits. M plus n is never 0, although after the difference quotient is simplified, it can be 0, or it can be one of infinitely many other pairs. We do know that m plus n is a factor of every term in the numerator. And that's pretty important to understand. It doesn't matter what function f is. In fact, it can be proved, as I mentioned earlier, in just about 2 or 3 lines using the Gabriel polynomial. But there is also a simple grade 8 algebra proof that shows this is indeed a fact. Okay, so now what we've done in lesson 6 is we've looked at how to calculate the slope of any tangent line using a geometric method. This is the secant theorem in the new calculus. It's known as the secant theorem, and you can read more about it over here in this section here on differentials and more on differentials, and also the first 4 lessons will have information on that and a proof that m plus n divides every term in the numerator. So that's pretty important, and that was what we needed to cover in lesson 6. In the next lesson we'll be looking at what is a natural average, because those are very important in the new calculus. In fact, natural averages are what make the calculus work, not limits or anything else. And I'm going to show you how that works in the next lesson. So this is the new calculus channel, and I'm John Gabriel. Glad you could join me. See you next time.